Hello, good morning, everyone. Welcome back to the Theory of Computation. This is the second video in the series, and it's focused on prerequisite content. Okay, obviously, as a field of sort of mathematics and slash computer science, obviously there's going to be some mathematics involved, and there are some maths that you are expected to know before we start the actual content. And I'm not going to look at all of the maths that you're expected to know today. It is decently hefty, not too hefty, and most of it is honestly taught in like a first course in Intro to University Maths. So, for example, things like functions, relations, and sets, which is what we're going to talk about today. Things like that, they're normally taught very early on at university, especially for a maths degree. I'm not sure about other degrees. But nonetheless, I'll still go through everything that you need to know. And some of it is not taught at an intro level, so maybe like and graph theory you need to be able to understand, and some other things with that as well. But we'll go through it bit by bit. So, if you are confident with this stuff, you can just skip to the next video whenever I post that. And if you're confident with all prerequisites, you can just skip through those. And by the time I post the first actual video on some actual theory of computation stuff, you can just get straight into it, okay? All right, so let's get started. Today, we're going to talk about sets. So basically, some very introductory set theory that you're expected to know and be confident with. Okay, because sets, they're really just fundamental objects, right? So you do need to be at least in mathematics. And if you want to sort of have a mathematical model of what a computer is, then obviously we're going to probably need to utilize these mathematical ones. We're going to need to utilize some mathematical objects, and it turns out that sets will be of use to us, or it will be helpful to know some set theory. Okay, so we'll talk about sets. In quite some detail, not too much detail, some detail in terms of like just all the very introductory stuff, nothing very like heavy on the set theory, and then we'll talk about sequences and tuples. Okay, so we'll introduce the concept of an ordered pair and a k-tuple and things like that, and things like the power set, Cartesian product, and just go through some examples. And these things should all probably be confident to you if you've really taken an introductory sort of university maths course. Most of these things are covered. At least most things I'm going to be talking about today are covered. So if you're confident with them, as I said, no need to watch this video. But without further ado, let's get straight into it. So, okay, so we're talking about sets and sequences slash tuples. Okay. Right. Okay, hold on. Let me just underline it like this. Okay. So, I guess the first question, we'll start by talking about sets. So the first question is, what is a set? Okay, I guess I can give you a definition for a set, and it isn't actually a bad one, but we don't need to be too rigorous about how we're defining sets at this point in time, right? The main thing is that we understand what a set is, because obviously there can be paradoxes can arise when you have specific types of sets, okay, which begs the question, what really is a set, okay, and then we need to be more specific about that. But for this case, and in the cases that will come up, we don't need to worry too much about those semantics, okay? At least to start off with, and it's not introduced at all in the prereqs of the textbook that I'm referring to. Okay, so I'm assuming that it won't be of issue, and so we can just accept and just be happy with an informal or more informal definition of a set. Okay, and so the definition that we're going to be using is effectively that a set is a group of objects represented as a unit. Okay, so I'm going to write that as well. So a set, right, is a group of objects. So when I say objects, obviously you might think, what is that? What it really is an object? I probably need to define that as well. Although I won't necessarily write down the definition, just know that an object is not really just a mathematical object. Okay, it literally is anything which I can put inside a set. Anything I want to that I can put inside a set. Okay, so it could be, and sometimes it's probably easiest to show, for example, numbers being put inside a set. And those are mathematical objects. Numbers are mathematical objects. So, and you can just chuck them inside sets, right? And that's fine. Those are types of objects that we can put inside a set. We can also put things like letters, right? A, B, C, D, E, F. Other symbols, even items, right? If we really want to. I mean, it's really open to interpretation, right? So by object, I just want it to be known that although it is a tiny bit ambiguous as to what I mean, really, I'm not just talking about numbers. I'm talking about things like numbers, letters, symbols, whatever you really want to put in there, right? Words, even other sets themselves, right? So you can just chuck sets inside sets, okay? And we'll see an example of that later, the power set, right? So, okay, so a set is a group of objects. Okay, a set is a group of objects represented as a unit. And so I probably also need to clarify what I mean by that. What does it mean to say represented as a unit? Okay, so, the best way to think of this is sort of as a storage room. Okay, so imagine that I didn't have a storage room. I just had lots of sort of items strewn out across the floor. I just had lots of items and stuff all over my floor. Then, obviously, that's not a unit, right? There's multiple different items. However many items there are, sort of, however many things I have in my room. But what I can do to those items is I can then put them inside one box and then effectively place, effectively I can place those items inside a storage room. And then I can count the storage room as a unit. And so effectively, every time I'm looking for one of those items, I just go to the same place, the storage room. And so effectively, my set is kind of like that, right? So without my set, I just have a bunch of objects just strewn out across my floor. And then I take my objects and I place them inside my storage room on my set. And now I just go to my storage room to look at my object. And that's basically my unit. Okay, because I'm going to the same place every time and it's just one place, it's a storage room. Okay, obviously analogously you could probably say, for example, which is what I was initially going to say, like you could place your items inside a box and then all of a sudden, because boxes are actually quite often used as analogies to sets. Effectively, you just put all your items into one box and now you just go to the box every time looking for an item, so it's a unit in that sense. Okay, so without the set, the objects are not a unit, right? You have to go to different places to find them. But once you put them inside the storage room, the box, etc., the set, then you can just look inside that one place as a unit. Okay. Right. So the second thing we need to clarify just in terminology. So obviously, well, not necessarily obviously, but hopefully you should have seen this before. That any object in a set is called an element or a member of that set. So any object in a set is called an element. All right, an element or a member of that set. Okay. And so this is just a standard terminology, okay? So if I have, for example, the number 4 inside my set, then 4 is an element of my set, or 4 is a member of my set, okay? So a set is like a storage room, okay? And effectively, it can store the number 4, in which case 4 is an element of my set, or a member of my set, whichever one you prefer, okay? They mean the same thing. Okay, we don't care too much about the specific word that you use, but preferably it's either an element or a member of that set, okay? There are probably other words that people use, right? But as long as you get the idea of what's being said, it's okay. Well, we need to be able to basically invoke a set, right? I've told you what set is, but how do I actually sort of introduce one? So I need to make that clear as well. So, well, we can describe a set. We can describe a set by listing its elements inside braces. Okay, that's one of the most common. Well, that is really just one of the ways. Well, yeah, one of the ways that we can list which we can invoke a set, right? Is literally just by listing its elements just outright in these braces, which I'll show you. Okay, so we can describe or invoke a set by listing its elements inside braces. Okay, so let's go through an example. So for example, I could invoke a set, capital S, and then I give them the first brace. So this is what I call a brace, okay? Just to be very clear about what I mean there. So that's the brace. And then I add in, a few things, whatever I want to put in my set. So in this case, I'm going to put only numbers, so mathematical objects, but it doesn't necessarily need to be the case as we discussed before. So I could put 7, 21, and 57 into my set, and then I close it off again with a brace like that. Okay. So this is a set. Okay. So that is a set, and then we say that set contains the elements. So it's a set containing the elements 7, 21, and 57. Okay, so the elements 7, 21, and 57. Okay. Awesome. Right, so hopefully that makes sense so far. Obviously, if you have any questions, let me know in the comments. But yeah, hopefully that should be fairly self-explanatory. You probably have seen this stuff before. Okay, and also just in terms of notation. So again, well, not again. So in terms of notation, we have a couple symbols to denote whether or not an object is actually in our set or is not in our set. Okay, or is an element of our set or not, or is a member of our set or not, whatever you want to use. Okay, so the symbols. So we have this sort of symbol here, and this same symbol with a line through it like that. Okay, denote set membership, so set membership and non-membership, respectively. Okay, so that effectively what we can say is that 7 is an element of, so that's how you would read this. Okay, we're effectively saying is an element of, or is a member of, is an element or member of. And then you basically say, you use the sort of either the capital letter, so if I say S, that's referring to a set S, namely the one I introduced before with this 7, 21, 57 thing here. I'm not sure if you can see that. Let me just, so I could be referring to a set of either the capital letter that I've used to basically name it, or I could just literally draw out the set explicitly. So I'm saying 7 is an element of that. Then effectively I can just draw in that set explicitly. So just put the brace there, and then do 7, 21, 57, like that. Okay? So that's what he's saying, that 7 is an element or is a member of this set containing these elements. Okay? So that is just formally how we write it, right? And obviously what we can also say using the other symbol is that 8 is not an element of, or is not a member of, the same set. So the set containing the elements 7, 21, and 57. Okay? So 8 is not a member of 7, 21, 57. No, sorry. I don't know what I'm doing. So 8 is not a member of, or a member or element of, let me just, sorry, I don't know why I'm rewriting all of that. You guys understand what it means effectively. It's saying 8 is not an element of, or is not a member of that set. Okay, and so what I was really trying to say there is I'm talking about that specific piece of notation here, which is just basically saying is not a member of, okay? Is not a member of, or is not an element of. Okay, so I hope that that is that's clear. And hopefully you've seen this stuff. It's not fairly standard set theory. Okay, but if not, don't worry though. Obviously, I hope you understand it nonetheless, and that is making sense. Right. So now we need to talk about subsets. Okay. So hey, you. I know. You want attention, good boy. Okay. So let's talk about subsets. So let A and B be sets. So now that we know what a set is and how to invoke it, we can effectively just suppose that we have these two sets, and I'm going to label them capital A and capital B. Okay, so they're two different sets. Okay, well, actually, not necessarily even different for the first part of this definition. Okay, so they could just be the same set but with a different label. So we say that A is a subset. Okay, is a subset of B, written sort of A and then that symbol B, right? If every member of A is also a member of B. If every member of A is also a member of B. Okay. And so this is obviously also the notation here as well for A being a subset of B. So this is how the way that you would read this is A is a subset of B. Okay. So you need to be familiar with this notion of subsets. Okay. One of the most crucial notions in introductory set theory is a subset. Okay. And the way that we define it is just by saying that A is a subset of B if every member of A is also a member of B. Okay. So for example, we could say that the set containing the elements 7 and 21 is a subset of the set containing the elements 7, 21, and 57. And that's because the set with the elements 7 and 21, okay, every element in this set is also in this set. Okay, so by our definition, we're happy. In other words, every member of A here is indeed also a member of B. And so A is a subset of B, and we can say that. Okay, but if I change, for example, this 7 here to an 8, and I kept everything else the same, then it's not a subset. Okay, then A is not a subset of B. Okay, so we can say that. We can also say, therefore, that 8, 21, right, is not a subset of the set containing the elements 7, 21, and 57. Okay, now obviously, even though 21 is indeed in that set, 8 is nowhere to be found. Okay, so the problem is that we actually have an 8 here. So every element or every member of A is clearly not in B, and so we can't necessarily say that A is a subset of B. And so we put this line through it here to say A is not a subset of B. Okay, right, is not a subset of. Okay, awesome. Right, but we also have things called proper subsets, okay? Because what you might also notice is that obviously the set is a subset of itself, okay? So every set is a subset of itself. So effectively, the set containing the elements 7, 21, and 57, right? That is indeed a subset of itself. Okay, it's a subset of the same set, okay? And the reason being for that is just because it adheres to our definition. Every element inside here, every member of this set is also a member of this set, okay? So, you know, it's pretty obvious to us that this is going to be true. That actually A is a subset of A is always true. Okay, so every set is a subset of itself, right? And so that's like a crucial thing. Okay, so you might also make that observation, right, that every set is a subset of itself. And so therefore we introduce a notion of a proper subset, which removes this. It just keeps the notion of a subset and it removes this possibility, right? So basically, well, let's write it out. And so A is said, sorry, some Skittles, to be a proper subset of B. Written as sort of A and the subset with a line through the bottom. Okay, so the line through this sort of horizontal line here. B, right? If A is a subset of B, okay, which you already know what that means, is a subset of B. So every member of A is also a member of B. And the two sets are not the same, okay? And A is not equal to B. Okay, and so also make sure that you are confident with this notation here, okay, that A is a proper subset of B, so you just have that sort of U shape which is flipped, and then with a horizontal line underneath it, okay, but then you put a line through that horizontal line, okay? It's just notation, okay? And it's just stuff that you can need to get used to. But don't get that confused with is not a subset of, okay? So that's sort of this, that's this sort of symbol here, okay? And obviously you don't need another symbol for is not a proper subset of, right? Because if it's not, if it's not a proper subset of, I guess actually technically they could be equal to each other, okay? But in all other cases, it's just going to be the exact same as is not a subset of, okay? So effectively, whenever you see that symbol, it just means is not a subset of, okay? And you don't really need another symbol for is not a proper subset of, okay? Because either you just say A is equal to B, okay? So either you state explicitly that the two sets are the same, right? Or they're just not, A is not a subset of B, and so you just write it like this, okay? So you don't need another symbol for is not a proper subset of, but you do need a symbol for is a proper subset of, and so basically we have that symbol here, okay? So just don't get that symbol confused with is not a subset of, because those two things look very similar, but they're different. So just to clarify again, we have three symbols for subsets, okay? So we have one symbol like this. This means is a subset of, is a subset of, okay? And A is a subset of B if every member of A is also a member of B, right? And then we have is not a subset of, okay? That's this. That is not a subset of. So this is the symbol for effectively, if A is not a subset of B, then effectively every member, not every member in A is a member in B, okay? So effectively there are some members in A that are not members in B, right? And then we have effectively the other symbol here. This is a proper subset of, is a proper subset of, okay? And that symbol there effectively just means that A is a subset of B, but A is not equal to B, okay? And then lastly, we have this symbol here for equality. And so that is basically, that basically represents A equals B. Okay, the sets are just the same, right? Or really what I should do actually is the equal symbol only, and that's just is the same as. Okay, is the same as. Okay, so we have these four symbols, okay? And is not a subset of, so if I do this, if I write this symbol, it just means it's not, A is not a subset of B, okay? If I want to say A is not a proper subset of B, okay, then I'm either going to have the case where A is the same as B, in which case I use this symbol, or I'm going to have the case where it's not a subset where I use this symbol, okay? So effectively, those four symbols are enough to talk about everything we care about, okay? Okay. Hello, my cat's here. You want to say hi? So another thing that's very important to note is that the order of elements in a set is not important. So the order of elements in a set is irrelevant. The order of elements in a set is irrelevant. In other words, I could order the elements in any way that I want to, okay? And my set will remain the same. It will remain unchanged, okay? So the order of elements in a set is irrelevant, okay? Is irrelevant, right? So in other words, if I invoke a set capital S, which is equal to the set containing the elements 7, 21, and 57, right? That's just the same as the set containing the elements 21, 7, and 57, okay? All I've done there is I've swapped the order of 21 and 7, but as I just said, for sets, that does not matter. You can swap the order of the elements, and the set itself is remaining unchanged. Kind of similar to how if I give you a box of items or a storage room, and I move the places of two items in my storage room, effectively my storage room is not changing. I don't have a different storage room. I still have the same storage room. I've just moved two items around inside it. Okay, same thing within a box, right? If you have a box and effectively you move the order of items around in the box, maybe you shake up the box or something, then obviously the order of your items will be completely in different orders, right? They'll be all over the place. But you have the same box. Your box hasn't fundamentally changed, okay? What's inside your box has changed, okay? But the outside of the box looks the same. Unless obviously it's like somehow punctured some holes or anything like that. But that's obviously, this is a theoretical item, okay? So that cannot happen with this. Right. Awesome. Okay. And we also need to clarify something else that doesn't matter, which is the repetition of elements. So we can repeat elements as much as we want. Okay, we can repeat elements or members as much as we want. Okay, without changing the set itself, obviously, without changing the set itself. Okay, so as an example, right? So e.g., right? The set, right, which I can invoke with a capital letter S, containing the elements 7, 21, and 57, right, is exactly the same set as the set containing 3 7s, followed by a 21, followed by a 57, okay? I could repeat the 7s as many times as I want to, okay? But I'm not actually changing the set that I'm talking about, okay? And obviously, because of the order rule before, that is exactly the same thing as the set containing the element of 21, followed, let's just say 2 21s, followed by 4 7s, followed by 3 7s, a 57, and a 7. So I've just tried basically mucking that up as much as possible to just show you that these things, it doesn't matter what order I put things in, how many times I repeat them, it literally does not matter. The set is going to be the exact same. All of those sets are exactly the same thing, okay? So that is a very important point, okay? It's a very important fact about sets, which does not always hold for other sort of objects that we'll talk about, okay? So it's a very important fact that the order of elements in a set is unimportant, okay? Also, I just realized this set is sort of annoying me because it's going down. So let me just sort of move it, make it slant a little bit more upwards. So we have 21, 21, 7, 7, 57, 7. Okay, awesome, right? Awesome. Okay, and so obviously those sets are all the same because we can repeat elements or members as much as we want without changing the set itself. Okay, and also we can effectively change the order of elements inside a set, and it doesn't really matter. Okay. 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 Awesome. So those are important points. But actually, we have another sort of structure that's similar to a set, which is called a multi-set. Okay, and multi-sets actually don't allow the repetition of elements whilst keeping the multi-set the same. Okay, so what I mean by that is multi-sets. Well, first of all, what's a multi-set? Multi-set is a set. A multi-set is a set, right, that does not allow for the repetition of elements. Okay, so as an example, right? As an example, you might have a multi-set. Let's just say it's S. So this is going to be a multi-set, right? Which is exactly the same in terms of format as the set capital S. Okay, there's really no difference. So you could either be referring, you'd have to write either multi-set or set to reference which one you're talking about. Okay, so this is obviously going to be in this case this is a multi-set, so you have to specify it. Okay, so this is a multi-set capital S. Okay, is not equal to. Okay, this is not the same as the multi-set. P, where P is effectively just a multi-set containing 3 7s, a 21, and a 57. So now that I've like invoked the multi-set, which is a different type of structure to a set with lots of similarities. Okay. Now that I've invoked this structure, I'm not allowing, okay, for the repetition of elements. In other words, what I mean by not allowing is effectively if I repeat any of the elements in a multi-set, then I'm changing it effectively. Okay. So for the best example there is just, for example, if I have a set capital S with the members or elements 7, 21, 57, and I repeat the 7, let's just say 3 times for the sake of argument, it could be 2 times, however many times you want. Okay. If I repeat it any more times than I have in the set capital S, then I have a different multi-set. Okay. Right. Okay, so that's just the sort of principal idea of multi-sets is that repeating elements changes the set itself, or changes the multi-set itself. Okay, but that's pretty much all I want to say about multi-sets then. Okay, that's pretty much it. Because maybe sometimes you might feel as if actually you want to have sort of repeated elements inside a set, for example, but obviously in a set that doesn't change anything. So you might invoke a multi-set, and by invoking a multi-set, you're now changing the actual, like, sort of, you'd have to change the label if you were to repeat any of the elements, because it's a completely different multi-set, whereas it wouldn't be a completely different set. So that might be useful later on, okay? But for now, just theoretically, hopefully you can grasp that concept. Right, and, we also have, although sometimes they can be very tricky, things called infinite sets. So obviously, as you would probably expect, an infinite set contains infinitely many elements, okay? An infinite set contains infinitely many elements. Okay. Right, and hopefully you have an idea already of this sort of concept of infinity. Okay, which is effectively just that if you had a set, right, with infinitely many elements, and you wanted to find, for example, what we call the cardinality of that set, which is just how many elements are inside it, then one way that you could do it is just by sort of counting up all the sort of going one by one, and then just incrementing by one. So you're counting basically the number of things inside your set. Right, so for example, for the set capital S with the elements 7, 21, 57, you would probably just go 1, 2, 3, right? You just count, this is 1, this is 2, and this is 3. And so the cardinality of that set could be 3, right? It is 3, okay? Because as we said, obviously the repetition of elements does not matter, okay? So obviously that, in terms of sets, that is the same as the set up here, okay? So both of those sets have cardinality 3, okay? So don't be fooled by that. But obviously in terms of multi-sets, this set has cardinality 3, and this set has cardinality 5, okay? Because they're different multi-sets. But effectively, when it comes to cardinality, right, with infinite sets, you could just try and go 1, 2, 3, 4, but you'd never reach the end because it extends as long as you'd like. In fact, not even longer than you'd like, longer than you could possibly imagine. Okay, so it just goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's no upper limit there, right? You're just going to keep counting on forever and ever and ever and ever and ever and ever and ever. Okay, you're never going to reach the end. And that's the concept of an infinite set, is that it contains these infinitely many elements such that its cardinality is just so large that you would never reach the end by trying to count one by one all the way up to, the end. Okay, so hopefully you're happy with that concept anyway. So it's a fairly well-known one, even for non-mathematicians, but there we go. But there are a couple of infinite sets which you should also be familiar with and happy with, one of which I basically just described to you, which is effectively the set of natural numbers. Okay, so the set of natural numbers is an infinite set. So the set of natural numbers, n, is an infinite set. Okay, and so we can obviously invoke that set as well. We need to do that to really talk about what it is. Described as, okay, so we have this sort of capital letter n is equal to, then obviously my first brace, okay, and then we start at 1, and then the next element in my set will be 2, 3, and then we put lots of dots there, okay? Because it's an infinite set, so these dots are just representing the fact that I just keep going on forever and ever and ever and ever and ever, okay? There is no end, there is no point at which if I was to just keep writing out each of the elements, I would never get to this final brace. It's such a big set that I could just never close it, because effectively there's so many things inside it. So what I use, instead I use these ellipses to say, like, it just keeps going on, then I put the brace at the end. Right. And we obviously also, hopefully you should also be familiar with something called the set of integers, okay? So the set of integers, and we denote that with a capital Z. I believe that's from German. If I remember correctly, it's something like Zahlen or something like that. I'm not 100% sure, but I think it's German or something for number. Not 100%. But effectively, the set of integers, and we label that set with a capital Z, is written as... okay, and then we have Z. Sorry. Z here is equal to, and then we do dot, 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 and then -2, -1, 0, 1, 2, and then again, all the way up to infinity. Okay, so a good thing to notice is that obviously via our early notation, the natural numbers is a subset of a set of integers. Okay, because if you can see here, my natural numbers start here and go on forever. Okay, so that will capture all my natural numbers. But the integers actually also give us 0, which is fundamental in many senses, right? When you add 0 to a number, you get the number itself. And then it gives you the negative numbers, which are also very important in many circumstances. Right? And obviously these negative numbers, I really mean negative integers, right? Because it's not going to give you negative a half. But it gives you some negative stuff here, which is very useful. And so yeah, we also have the set of integers. Obviously it's also an infinite set, right? And it extends infinitely to the left and infinitely to the right, whereas the natural numbers only extend infinitely to the right. Like we have a smallest element of the natural numbers. We don't have a smallest element of the set of integers. Okay? And yeah, and those are just two sets that hopefully you're well acquainted with. Okay, we're not going to go through all number systems and that kind of stuff now, but just to give you an idea of what really an infinite set, an example of an infinite set is, hopefully though these concepts of number systems, natural numbers, integers, rationals, irrationals, things like that, those should be you should be pretty happy with those. I'm not sure if you really need complex numbers for this. I don't think you do, but potentially it may come up. So potentially you also be happy with the notion of a complex number. Okay, right. So we have sets with 0 members. Okay, so it might seem stupid to you, but actually occasionally it does come up. So the set with 0 members, okay, is referred to as the empty set. With 0 members is the empty set. Okay, and the way that we denote the empty set is just with that sort of phi. Okay, so like this, written with that circle with a line through it. Okay, so you should really be familiar with all this notation I've spoken about today. Okay, if not, you're going to have to get used to it. It does come up. Right, so that's just the empty set. So the empty, for example, if I were to write it out, I'd have phi is equal to 2 braces, then nothing inside. Okay, so that's it. That's the empty set. Pretty boring, but there we go. It's just a set with nothing inside it. A box, an empty box, if you will, an empty storage room. Right, pretty useless storage room as you might think, but actually it does come up on occasion. We also have a name for the set with a singular element, with one element. So the set with one element is occasionally referred to. One element is occasionally referred to as effectively a singleton set. So the set with one element or member is sometimes referred to as a singleton set. Okay, and we actually also have a name. And so if you are wondering what a singleton set would look like, if an example of one, there are infinitely many examples. An example of one would just be the set with the element 1 inside, okay? Again, it's kind of boring, just like a storage room with one thing inside it, a box with one thing inside it. But there we go, we have names for these things, okay? And we actually also have a name for a set with 2 elements inside. We're obviously not going to do this for all numbers, but just these 3 are things that you might hear. So 0, 1, and the set with 2 elements. I say the set as if it's uniquely defining something, but what I really should say is a set with 1 element, because it's infinitely many, and similarly, a set with 2 elements. But obviously there's only one empty set though, right? So there's infinitely many singleton sets, but one empty set. So a set with 2 elements inside is called an unordered pair. Right? So a pair because there's 2 elements inside, and unordered because we can swap the order as much as we want, and the set remains the same. Okay? And because it's a set, obviously we can also repeat the elements as well, but that doesn't come into the name. So the name unordered pair is just basically representing the idea that we can just swap the order of the pair and it doesn't matter at all. Okay, so that will contrast that later with something called an ordered pair, whereby the order matters. So a set, for example, can represent unordered pair. So 1, 2, this is an unordered pair. Okay, because effectively in set terms, 1, 2 is the same as sort of the second thing, the elements 2, 1. But later on we'll introduce an unordered pair, which you might think of as a coordinate in some senses. So 1, 2, this is an unordered pair notation, is not the same as 2, 1. Okay, so those two things are different because the orders swap. But in set notation it is. And obviously, as I said, we can also repeat the 1 here as much as you want, but that doesn't really come into play, right? You're not really doing anything by doing that, so it doesn't really come up. But obviously, if you're wondering, then it's also something that you can do, as we've already spoken about before. Okay, so there's another way that we can sort of invoke a set or introduce a set, right? If a set is sort of very large, then we can introduce it by effectively a rule, okay? So we can effectively say, I want to construct a set of all elements such that this rule is satisfied effectively. So when we want to describe a set containing elements adhering to some rule, right? We can say that we can say, okay, for example, my set capital S is equal to the set of all n such that, rule about n. Okay, so this is a valid way of introducing a set based off of a rule about the elements in that set. Okay, so I'll give an example of this, which is as follows. Okay, so for example, we could define a set P such that, okay, P is equal to the set of all n, right, such that n is equal to m squared for some m in the natural numbers. For some m in the natural numbers. Okay, sorry. So this is a valid way of defining a set. So instead of just writing out all the elements, which is impossible in this case, because this set P is actually a set of all perfect squares. So like, for example, 1, 4, 9, 16, there's 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, so on and so forth. This is a set of all perfect squares, right? I couldn't write those out, right? I couldn't write all of them out, it's infinitely many. because the set of natural numbers is an infinite set. So if I could choose this infinitely many choices for m, and so there's infinitely many elements inside my set P, right? And so it's actually better in this case to describe this set by this rule, okay? Because this actually gives me the same information, but I don't have to necessarily write everything out, right? I can just give you a rule, which is that n is a perfect square. So n is equal to some natural number squared. Okay, that's basically what this rule is telling us. And then we have a set of all n, effectively. This line here, you could read that as sort of such that. Okay, that's how you can read it effectively. Or you could just perceive it as a break, so it's like n break, and then you give the rule. Okay, that's fine as well. But if you want to have that sort of sense of coherency, then you could also read it as such that. And I think most of the time it will work, right? And you can certainly sort of construct these sets under both interpretations, right? So for example, if you wanted to construct the set of all nat perfect cubes, you could perfectly fine just think of it as such that, right? You could perfectly fine say, okay, I want the set of all cubes, so I have the set of all n such that n is equal to m cubed for some m in the natural numbers. Okay, that's fine. That reads perfectly fine. Equally though, you don't have to do that, and you could think of it as just as a break. So then you just have the set of all n break, and then you give a rule, n is equal to m cubed. Okay, and that's fine. Perfectly fine. However you want to read it is however you want to read it. Okay, right, so now we need to talk about the union and the intersection. So, given two sets, right? Given two sets, A and B, right? The union of A and B, written, so this is another piece of notation for you, A with a U and then B, is the set, effectively achieved, by combining all of the elements of A and B, by combining all of the elements of A and B into a singular set. Okay, so effectively what this is effectively analogous to is me having two storage rooms, okay, full to the brim, and then getting a larger storage room and then emptying out those two storage rooms and putting everything into that larger storage room. So then I have two storage rooms and I'm making one big storage room out of those two storage rooms. That's what the union is doing. It's taking all of the elements, all of the members of my individual sets and combining them into one big set. You're just taking two things, you're clumping them together into one. Okay, so that's how you can think about the union. Right. Okay, and we also have something called the intersection. Okay, so the intersection of two sets, okay, A and B, right, which is written A and then sort of the upside down U, so it's going to be A and B, okay, is a set of elements that are in both of A and B. That are in both A and B. Okay, so that's effectively how my intersection is working. Okay, so it's like having my two storage rooms, and then I'm looking in those storage rooms for things that are the same. Okay, and if I find two things that are the same, I take them out of my storage room and I put them into a new storage room. Okay, well technically what I'm doing with sets is I'm keeping them in my storage room, but I'm like making a new storage room. But effectively you can think of it as I'm taking them out and I'm placing them in a new storage room. Okay, as one thing, effectively. Well, it doesn't actually matter because I could have repetition of items and it's the same. Okay, because it's a set, so you can repeat the items as much as you want to. So effectively, what I'm saying is that you have these two storage rooms. You take out all the things that are the same in both storage rooms. So let's say that there's a teddy bear in one of them. Okay, and you find a teddy bear in the other one. Okay, so that's a repeated element, effectively, a repeated member. So you take those two teddy bears out and you place them into one new storage room, which is the intersection storage room, effectively. Okay, so that's how the intersection of two sets works. And sort of lastly, you want to talk about the complement. Okay, so the complement of A. So the complement is just on one set. So the complement of a set A, right, written as sort of A with a line on top. Okay, at least in this case, you might also see it as sort of A with like a sort of a apostrophe up there or whatever. I mean, it's really really open to the notation kind of the complement. But as long as people know what you're talking about, again, it's fine. Just make it clear if you're going to use it. But within a textbook that I'm referring to, they use this sort of symbol, A with a line on top, horizontal line. So the complement of A, written with the A with the horizontal line on top, or A apostrophe, is effectively the set of all elements under consideration that don't lie in A. Okay, is the set of all elements or members that we care about. So that we care about, okay? I'll explain what I'm talking about in a second. That we care about. That don't lie in A. Okay? So, effectively, what do I mean? So let's suppose that I'm considering the set of all prime numbers, for example. Okay, so a prime number is a number whose factors are just itself and 1. Okay? So, for example, 13 is a prime factor. It doesn't have any, sorry, is a prime number. It doesn't have any other prime factors, right, other than itself, effectively, right, because 1 is not prime. Okay, so the only sort of factors of the number 13 are 1 and 13. You can't sort of, there's no other prime factors, right, to consider other than 13. And so if you consider A to be the set of all prime numbers, right, well, actually, no, sorry, let's just say that we're dealing with all prime numbers, okay, that's like the numbers that we care about, okay, and the set A is the set of all odd prime numbers, okay, so you would put 3, 5, 7, 11, 13, all of them, pretty much, in there, okay? So then the complement of A would just be 2, okay? Right? Because the elements that we care about are the prime numbers, right? So all numbers that have factors that are just themselves and 1, effectively, right? So all numbers that can be factored, that cannot be factored other than into a product of itself and 1. So for example, 13 is just 13 times 1. You can't really factor it any other way. 11 is just 11 times 1. There's no other way to write it, okay? So that's a prime number. Those are the only numbers that we care about, okay, in some specific case. And if we have a set A, which is the set of all odd, so effectively a storage room of all of the odd prime numbers, and you just chuck all the odd prime numbers in there, then A complement is the set of all prime numbers that are not odd. So the set of all even prime numbers, which is only 1, 2. Okay, so 2 is an even prime number. Okay, and that's placed in the complement of A. Okay? So, but obviously, you could argue, if I didn't say all of the elements that we care about, you could argue that actually there should be like other stuff in the complement of A as well. If I say A is a set of all odd prime numbers, then A complement is equal to 2. That's wrong. Because technically, like, if you say everything that's not in the set of all, if you define the complement of a set as the set of all elements that don't lie in it, then technically you could also have, like, for example, teddy bear, the word teddy bear outside of the set, or some ridiculous thing like some other, like, non-numbers, just like letters, symbols. You could add whatever you want, right? 2 as well. But like anything, you could technically put anything you want. You could put 1, 2, and just like other random stuff like symbols and letters. So obviously it's a set of all members that we care about that don't lie in that set. Okay, and typically it's quite obvious that like that is the case. Okay, I didn't really need to go off on a tangent about that, but you know it's just important with definitions in maths to make sure that you're 100% certain what something's talking about. That there's no caveats, because occasionally what you'll get, right, is people will be like, oh, but what about in this case? And you're like, oh, I didn't actually think about that case, and actually my definition is invoking this sort of plot hole, if you will, not plot hole, not a movie, but you know what I mean. Right? So effectively this sort of loophole is invoked by your definition, which you don't want, okay? And that would happen. If we didn't say all the elements that we care about that don't lie in A, then effectively we get this loophole, right? Because then if I have the set of all odd prime numbers and I take the complement of that set, then it's effectively just everything else. Not only 2, but just everything else, right? So, you know, we need to be specific. We need to be careful about what we mean. Right, and we also have these things called Venn diagrams. I'm hoping as well that you've seen these before. So Venn diagrams represent sets as regions enclosed by circular lines. Okay, so for example, let's just say let T be the set of all English words starting with a T. So let T be the set of all English words starting with a T. So obviously the W with a dash next to it, that's just my way of writing with. Hopefully you can get that. Starting with a T. So the way that we would represent this in the Venn diagram is a circle. So we have a circle here. We label it T, and then each of the things inside my circle are all of the words. So for example, one thing that might be inside my circle is the word terrific. Okay. Another thing that might be inside my circle is the word terror, right? Another word might be the word try, so when you're trying to do something, right? And also the word theory, okay, might be in there. All of those are valid elements or members of my set, right? Because they're all English words that start with T, right? Obviously, there's not only 4 elements in that set. There's going to be a lot more elements in that set, and it also depends on necessarily what you count as a word and like whether it's in a dictionary or whatever. Okay, but ignoring those semantics, right? Hopefully, you can see this is a way of representing a set. It's like a circular now. Obviously, instead of a storage room, which you might think doesn't necessarily have to be circular, right? Instead of that, obviously now we just have these circles, and we place elements or dots inside those circles that represent the members of that circle or the members of that set. So in this case, T is our set, so you represent it with a circle. We put all the dots inside that set are just the members of the set. So one of the dots might be terrific, try, terror, theory, and then obviously you can have lots and lots of, probably there'll be many, many, many other dots, okay? In this specific circumstance, I'm not sure how many, but there'll be a lot more, okay? And then effectively you just have to put a dot for every single one of them, right? And you can represent a set in that way pretty easily, okay? So that's an example of a Venn diagram representation of T. Okay, so this is a Venn diagram. That is a Venn diagram representation of T, set T. Okay? Right. Awesome. Okay. So similarly, and now I'm doing this for a reason, you can just also invoke a similar set. So similarly, right, we're going to invoke a new set, Z. So let Z, right, be the set of English words that end with a Z. Okay, so a Venn diagram representation of that set might be as follows. So it will look like sort of a circle, right? And then you just have some words in there, right? So for example, jazz, right? That's an English word that ends with a Z. Quartz, okay? And of course, many others, right? I'm sure. Okay, so this is just a Venn diagram representation of English words ending in Z. So Venn diagram representation of Z. Representation of Z. So all the English words that end with a Z. Okay, so now what we can do is we can actually represent effectively Z and T in one diagram. Okay, and if I want to represent Z and T in one Venn diagram, okay, then I have to be careful about how I do that. Okay, because if I do something like this, so that's my Z with all the words in it, and then I do something like this, that's my T. That's not actually combining Z and T, but you can't. This is not actually the correct way of representing those two sets inside a Venn diagram. Okay, you can't just sort of put them next to each other like this. They actually have to overlap a little bit, right? Because there is some overlap, right? There are some English words that start with T and end with Z. Okay, and so obviously, if you were to put sort of those two into one sort of big picture, you would indeed have an area where these two sort of circles meet. Okay, so obviously then you do something like this. Okay, so they overlap over here, right? And then what's inside that overlap are all the English words, which there is one that exists, namely topaz. Okay, topaz is a word that starts with T and ends with Z. Okay, so within that set, obviously, you're going to put all the English words that start with T and end with Z. Okay, I'm not sure how many there are, but definitely there is at least one. So for example, here, you would put the word topaz. And even if there is 0, it's still good practice to basically overlap these two sets like that. Okay, so whenever you want to represent the two sets in one, or, any two sets you want to represent in one picture, we always it's just formal, okay, it's just the right thing to do, to basically have this overlapping region, okay? We have to introduce it because there could be a possibility that there are elements that are in both sets, okay? And this region here is actually the intersection, okay? So when we defined the intersection of two sets before, this region here is the intersection of the two sets. So namely, this region here is Z intersect T. Okay, so that is the intersection of the two sets, Z and T, right? So hopefully that's familiar with you. But effectively, you can't just, whenever you want to combine two sets to give one set, right, or you want to basically represent Z and T all at once, you can't just sort of shove them next to each other. You have to have this overlapping region, right? Even if there is no overlap, it's just good practice because in general there will be, well, not necessarily in general there will be, but in many cases there will be some overlap between the two sets. Okay, so we need to be able to represent that, and this is how we do it, okay? And yeah, okay, and so this is obviously going to be a Venn diagram representation of Z and T both at once. Okay, right, awesome. Okay, and the last thing on sets is just as follows. For two sets, A and B, okay, the Venn diagrams below, okay, represent A union B and A intersect B. Okay, respectively. Okay, so basically in that order. Okay, so A union B is going to look something like this. So you have a set B, okay? And obviously whenever you want to combine, whenever you want to sort of label those two sets and like put them into one, you always have this overlapping region here, always, okay? A union B is simply just going to be this, right? Okay. And A intersect B is going to be this. Okay? And you also have, obviously, the complement of A. Now, the complement of A, okay, is going to look something like this. So everything that's not in A, so just this. Okay? And obviously, everything that's not in A that we care about. Okay? So there might be some things that we care about that are not in A or B. So in that case, we have this other box, this third box, which is things that we care about, but that are not in set A or set B. In which case, the complement of A also will include those things. Okay? Right. Okay. So that's basically it. That's all the set theory that you need to know. I'm thinking whether or not actually I end it there, because that's already taken up like 50 minutes or so. Okay, on the video it'll only be like 30 minutes, but I think actually I stop it there for now. Even though I said we're going to look at sequences and tuples, that'll be for next time. So next time we'll look at sequences and tuples, and we'll look at effectively things like ordered pairs. So obviously today we introduced the notion of an unordered pair. Next time we'll introduce the notion of an ordered pair. We'll also introduce k-tuples, effectively the Cartesian product, the power set, and just go through a couple of exercises. Okay, so that being said, thank you guys very much for tuning in today, and I'll see you guys in the next one. Goodbye.